All right, hey. So this is chapter 7, chemical quantities and reactions. Uh, just a couple updates. I have decided how we're going to do the test. I'll post an announcement on that and maybe a video talking about what you need to know and how it's going to work. I've also split up so I got a bunch of questions about lab yesterday. The lab is, there's 3 PDFs and 3 Word documents. They're essentially the same thing. So the Word document is just something that you can fill out and submit back in. The PDF is for you to keep, and it's a little more detailed, but it's the same procedure and questions that are on the Word document. Okay. So with that, I'm also going to post a video, some more videos on ions and valence electrons, formal charge, so we can get some practice on that, because it's going to be very important going forward. You'll see today we're doing some chemical reactions in which knowing the formal charge will really help you balance equations. Okay, so let's get into it. Let's see. All right. So the first thing is numbers. All right. So when we talk about chemistry and atoms, molecules, whatever, you're not going to hear us say there are 6 to the power 34 hydrogen atoms in this jar, right? It's just it's difficult to deal with, and as I said, we use scientific notation to reduce the amount we have to write, but sometimes dealing with numbers so large like this in every case would just be impossible. So they've come up with moles, all right? And what a mole is just a representation of that really big number, okay? So if I say I have a mole of something, I actually have 6.02 times 10 to the 23 of that substance. All right. If I say I got a mole of pizza, that means I've got 602 with 21 zeros behind it, numbers of pizza. So that's how we kind of represent these large numbers. Let's do a couple practice problems, just kind of go over it. So it says here, it works an example for you here. Let's do this one down here. 1.75 moles carbon dioxide. Okay, and it wants to know how many molecules of carbon dioxide I have. Let me pull up my iPad. Okay. So it says I have 1.75 moles of carbon dioxide, and it wants to know how many molecules. Alright, so we said Avogadro's number is 6.02 times 10 to the 23. Alright, and then that would be just a number. So this is unitless, right? I mean, the mole is the unit. This number, it just represents a number, but there's no units on the back of it. It's that number of whatever I'm talking about. I can have a mole of hydrogen will be 6.02 times 10 to the 23 hydrogens, right? And then a mole of water will be 6.02 times 10 to the 23 waters. So it's just a number. There's no units, but on the bottom, so 1 mole. Okay, so and it wants to know the number of molecules, which is also unitless, right? So I don't have a unit in my solve side right here. Okay, that shouldn't be equal. That should be just yeah, right? I don't have a unit. There's no unit right here. So if I want to find this, I can just multiply it, all right? times 1.75. Let me erase all this. Moles. My moles will cancel, and I'll just get the unit, and that equals, got a calculator here, 6.02 times 10 power 23. How do I do that right here? 23 equals, and then times, so I do them individually just so that it doesn't get messed up on order of operations. 1.75 moles equals, answer should be 1.05 times 10 to the power 24. 1.05 times 10 to the power 24. Double check that. 1.05. I rounded down because of that 3. And E plus 24 is the same as 10 to the power 24. Okay, so that should be right. Let's check our book. Next page. 1.05 times 10 to the power 24. Okay, so that's kind of how you do that. Let's go the opposite way. All right, so say it gives me the molecules. Clear here. Say it gives me the molecules. Say it tells me I have 7.6. Let me write this back up higher. 7.63 times 10 to the power 25 molecules. Now this could be atoms as well, right? I could have 7.63 times 10 to the power 25 atoms of something. All right. So, and now we want to solve for mole. So let's do our conversion. We said 1 mole is equal to 6.02 times 10 to the power 23. Right? So if I want to solve and get the moles on the end, don't do that. The moles on the end, I'm going to need to multiply by a number of molecules. Okay? See how my moles on top? So really I wanted the molecules to be on opposite sides. So I will divide 7.63 times 10 to the 25. I'll write molecules in right here so you can see what I'm talking about. So molecules, I just do that and then divide it by 6.02 times 10 to the power 23 molecules. Sorry about the writing, I'm trying to do it fast. Alright, so let's enter all that into the calculator, and this is going to be interesting. I want you to see how I work the calculator here, because you could get confused when you're doing all this scientific notation. A lot of people like to put it in the parentheses. Everybody's calculator is different though, so it can get messed up. I try to use a method that works for me, and it works on every calculator. Okay, so the first thing you're going to want to do is just do one thing at a time. So the first thing I'm going to do is do 7.63 times 10 to the 25. Go ahead and get that in there. Clear all this. 7.63 times 10 to the power 25. Press equals. Go ahead and clear that out. Alright, so now let's go back to our problem. Now I need to divide by 6.02 because it's on the bottom. So I'll just divide, but then I'm going to hit equals again. Go ahead and clear that out. Divided by 6.02 equals. Okay, so that's cleared out. Now, and kind of as I'm going, I'm marking these out. So I've used that, I've used that, I've used that. Now, still left on the bottom, even though it says times in front of it, in the overall equation, it's dividing. So I will also divide by 10 to the power 23. Divide 10, 23 equals, okay? So that would be 126.7 moles. We'll go back and see what significant figs is. 3 sig figs, 7.63 right here, and then 6.02 right there, so 3 in both of those. 127 moles. Okay, so that's how you do those problems. Let's move on to the next. All right. All right, so and notice here, I don't know why that popped up, that in a molecule you'll have different amounts of different numbers of atoms. So whatever this is, what is this? Aspirin. Okay, so in aspirin I have 9 carbons, 8 hydrogens, 4 oxygens. If I were going to say I have 1 mole of aspirin, I'd have 6.02 times 10 to the power 23 aspirin. All right, but if I were talking about the number of carbon atoms in there, so it'd be 6.02 times 10 to the 23 times 9. Okay, so just kind of bring this back around. So 1 mole of aspirin has 9 carbons per aspirin. So then, and this is not talking about the aspirin pill, this is talking about the individual aspirin molecule. Okay, so 9 carbons per aspirin molecule, I'll write that in there. Okay, so that means in the total I have 9 moles of carbon. Okay, so that's how you need to think about that. A molecule can be broken down into individual atoms, and it will be in chemical reactions, right? I move 1 atom at a time, and then over time the whole number decreases, so you're moving moles of atoms in reactions. All right, and that's what we're talking about today, so need to make that clear. I'm sure they'll have some problems for this in mastering chemistry, but most of the times we're not trying to figure out the individual number of molecules. We use the mole, let me switch back, we use the mole to tell these large numbers in an easier way. So most of the times you'll just be dealing with moles. You'll say I have 0.05 moles of this, I react it with a half a mole of this, something else, and it creates 0.25 moles of this. All right, so another way we use moles is in molar mass. Okay, so let me bring up this. You'll see here on the periodic table that one of the things listed here is a molar mass, and for silver it's 107.9. So what that means is that every mole of silver, 1 mole of silver equals 107 grams. 107.9 grams to be exact. So when I set this up in my equation and I say the molar mass, it might be 2 big M's like that, of silver equals 107.9 grams per mole. Remember, when I say per, that means the next things go on the bottom. So 107.9 grams per mole. Now, how is that useful? So we can use the grams per mole as a way of back calculating the number of moles we have. If I have a weight in gold, right? I have, let me pull up a periodic table so y'all can see how I'd figure that out. Where's it at? Display. All right, so gold is AU right here, 196.97 grams per mole. So if I were to, what'd I say? Let's call it 197 grams per mole. Clear, clear. Okay, so gold, no, that's not gold. Gold is 197 grams per 1 mole. So if I have, let's say a pound of gold would be, let's just say I have 28 grams of gold. And I want to know how much, how many moles that is. Okay? So just like any other problem, we'd set it up in a way that we could cancel out the grams and end up with the moles. Okay, so in order for me to get to, I have 197 grams per mole here, all right? I have 28 grams here. So the grams are on the same side. You can imagine this is over 1. So the grams are both on top. When I set my problem up, I'm going to want to write it on the opposite side. So 197 gram, actually, start here. 28 grams, and then times, I'm going to flip it, 1 mole, 197 grams. Okay, because I want my mole to be on top, and I'll show you just a second. Like if I were to do, let me get my eraser here. If I were to start the other way, 197 grams per mole, 1 mole, right? And then say I put my 28 grams on bottom over here. I flipped the wrong one, essentially. Then what I'm going to end up, yeah, my grams cancel out, but I end up with my moles on the bottom because I can't just move it to the top. So whatever answer I'd get, let's call it 8, it'd be 8 divided by 8 per mole. And we're not wanting a per mole, we're wanting mole. So keep track of that in that way. If it's on the bottom, it has to stay on the bottom in the answer too. So carrying on right here, 28 divided by 197. 28 divided by 197 equals 0.14 moles. 0.14 moles of gold. Okay, so that's kind of how you use molar mass, and you can work both ways. The biggest part is just setting up your problem, right? Figure out what it asks you for. If it's asking you for moles or grams or molar mass, right? Go ahead and put your unit on this back side. So say it's asking for molar mass. It says find the molar mass of 10. Okay, well on the answer side, I'm going to go ahead and write in grams per mole. Okay, that way I know what I'm solving for, and I know what needs to happen over here so that I end up with grams on one side and moles on the other. Okay, I don't even know, maybe it's like that, I don't know. But see, my grams cancel out and I end up with the same units on this side as I did on this side. So keep track of that, and it should help you solve these problems more easily. All right, what did I lose? Where are we at? All right, let's see. So chemical changes, I'm kind of jumping back and forth. I calculated the molar mass, but we're getting ready to get into reactions, so I want to talk about that a little bit. Um, so a chemical change, we did a little bit of this in lab yesterday, and it was kind of teaching you that these different things can happen when we have a chemical reaction. So one of the things is a change in color. We did the silver and the chloride, right? You saw it was clear, the salt water was clear, the silver water was clear, and then when I mixed them together, it turned white. So that was evidence of a chemical reaction just based on the change in color. But what was also happening was the formation of a solid. You couldn't necessarily see it in the lab video. In real life, it's much more evident. So that white is actually solid particles that are floating around in there. All right. If I were to let that sit for a long time, those particles would fall to the bottom. I'd have water up top, essentially, maybe a little silver and chlorine still floating around, but all the silver chloride, the one solid pieces, would fall to the bottom. Okay, so that was another piece of evidence that a chemical reaction had occurred. Formation of bubbles. Some of these reactions, you probably saw some in the lab yesterday as well, will form bubbles when they react. And then one more is producing some kind of heat. All right, so like right here in the example, it says methane gas in an outdoor heater burns with a blue flame. So you might be tricked into thinking that this is heat produced or heat absorbed, but it's not. The change in color is the signal that you're looking for the chemical reaction. All right. And it also forms a gas, which you don't know that just looking at it. So most of the times when we talk about gas formation, you'll see it like in practice, you'll see it like little bubbles coming up in a mixture. It could definitely be like smoke bellowing out. That'd be an obvious sign of a chemical reaction. Okay, bleach removes stains from a shirt. That's a color change. An example of a heat will be the mixing of an acid and a base. So in lab, I would have you mix sodium hydroxide and hydrochloric acid, and both of them are at room temperature, but then when you pour them together, it gets really hot in your hand. All right, that is a chemical reaction that produces heat. All right, an exothermic chemical reaction. We'll talk about that in a second. All right. So yeah, roll through here. I posted all these on Cougar View, and like I said, they're pulled straight from the book. So, and when you open it up in Cougar View, you won't have these missing pages. I don't know what happened there, but so yeah, use yours through Cougar View, and you shouldn't have any problems. What else? Let me know if you do. I'll try to get whatever pages are missing. I don't know why it's doing that. Okay. Anyway, back to the text. Let's see where we're at there. Okay, so we talked about chemical reactions. Now we're going to start writing chemical equations. All right. So chemical equations are the way we express what's going on in nature. You'll see here it's talking about two wheels versus plus a frame equals a bike. That's just kind of showing you the reactant side of an equation versus the product side of an equation. And I mean, it's not a great example because honestly, we could be taking the bike apart. The reactant could be the bike itself, and then I break it down into two wheels so I can sell it off for parts or whatever. Now my products are the wheels and the frame. Okay, so it can go both ways. It's really just based on which side they're set up on. So this here is carbon plus oxygen will give carbon dioxide. All right. Reactants, products, balancing equations. Okay, so let's do some of this. iPad. All right, so the book gives you an example. H2, which is a gas, plus O2 yields, and that's what this little arrow, I like to say yields, so if you hear me say that, we're going across that little arrow right then. All right, so remember reactants, products. All right. Now, this equation is not balanced, and I'll show you why. So, over here I have 2 oxygens, and over here I only have 1. And that's not how we do chemical equations. So, I need to figure out a way to make both sides have equal number of atoms. I need to have the same number of atoms on this side as I do, and the same number of hydrogen on this side as I do on this side. I also need to have the same number of oxygens on this side as I do on this side. So the easiest thing to do would just be to multiply. Okay, I can't really split oxygen and hydrogen into singles because that would require energy. Remember I said the breaking of bonds produces energy or takes energy. Okay, they're low energy bonds, and so I had to put energy in there to get them apart. All right. So instead of splitting it apart, let's double this side here. Okay, so I'll just say 2H2O. Okay, now if I put a number in the front, that means I'm multiplying everything in here by 2. Okay, so 2H2O actually means 4 hydrogens and 2 oxygens. Okay, so just keep that in mind. A coefficient in the front means I'm multiplying everything by that number. Alright, so let's go back to our equation. Plus, not plus, yield. Alright, so now I need to match the same number of atoms that I had on this side over here. So now I said I have 4 hydrogens. Let's do, remember I can't split the molecule up and just do 4H because it takes energy to break that bond. So I'm going to leave the molecule like it is, and I'm just going to put a 2 in front of it as well. Alright, because that also makes 4 hydrogens. Plus, and then I have 2 oxygens on this side and 2 oxygens on this side. Okay, so double checking, 4 H's over here, 2 oxygen right there, 2, yep, 4 H's there, 2 times 2, right? It's 2 hydrogen molecules, 4 hydrogen, and then 2 waters right here. 2 from the coefficient here, and then 2 O's, 2 oxygens on this side. Okay? Yep, let's do one. Well, let me roll in the book and we'll do one a little more difficult when we come to it. Alright. So, here you'll kind of see some examples of how we deal with coefficients. If the number's behind it, it's part of the molecule, okay? So, like Fe2, there's 2 irons in there. S3, there's 3 sulfurs. If I were to put a 2 in front of all this, it'd be 2 times 2 irons, so 4 irons, and 2 times 3 sulfurs, making 6 sulfurs. Okay, so you see how coefficients and exponents are different. Alright, the exponents mean that it's incorporated into the molecule. I can't break it apart easily. If it's a coefficient, that means it's separate molecules. I have, like in this problem here, when it gets to 2, I've yielded 2 separate iron chlorides. Each iron chloride with 3 chlorine atoms in it. Okay, so 6 total chlorines divided among 2 different iron chloride molecules. Alright, I said again, I'm doing a lot. Alright. Steady check. Alright, balancing chemical equations. So this is what we've been doing. I did it with the hydrogen here. Let me get it back up and we'll do some more. That's not difficult enough. Let's do one a little harder. So sample problem 7.8. sodium phosphate. I'm going to do that on the iPad here. You can kind of see what's going on. So it's Na3PO4 plus magnesium chloride. Yields, and I'm going to come down right here, just kind of indent Mg3. If it's in parentheses, that means it's one of those polyatomic ions that we were talking about. So it has to keep it separated from the rest. It's going to have its own exponent. Sulfate is SO3 or whatever, SO4. And then phosphate, PO4. Off the top of my head, I can't think of more examples, but that ammonia, NH4. So you'll see these polyatomic ions in parentheses. They're their own little part of the molecule, okay? And in this one, I actually have 2 phosphates connected to 3 magnesiums, all right? But this is all one molecule, plus NaCl. Oh, we also need to talk about these little symbols behind the equation. So you're going to need to express that. It's really easy though, so I'll get back to that here in just a second. Let's do this problem first. All right, remember what I said? We're trying to balance the numbers on both sides. So let's just keep a tab of the number of atoms I have. 3 sodiums, 1, this is PO4. I have 1 phosphate. All right, 1 magnesium and 2 chlorides. Okay, so now on the other side, I have 1 chloride here, 1 sodium here. I have 2 phosphates here, 3 magnesiums here. So let's lowest common denominator or least common multiple. For these would be, looks like 6, right? So if I say 6, 3 can go into 6, 1 can go into 6, 1 can go into 6, 2 can go into 6. Looking up here, 3 can go into 6, 2 can go into 6, so on and so forth. So let me clear all of this. Said 6 is going to be our least common multiple. Let's start with the stuff that has a 3 on it because that's the oddest number to deal with. So in order to make 6 sodiums, I need to do 2 Na3PO4. Okay? Let me make sure I'm copying that right from the book. Yeah, okay. Alright, and so then on this side, 2 is my lowest, so let's do 3 times, and I'm trying to get 6. I'm looking right here. Chlorine has 2 chlorines right there. So 3 times 2 would be 6. That would get me up to 6 chlorines. 3 magnesium chloride. Now let's do a yield. On this side, I have Mg3, so it'd take 2 Mg3s to get a total of 6. Well, hold on. I don't even need to because I have 3 Mg on this side, so 3 Mg works there. I have 2 phosphates here, so that matches. Let's just write that one how it is, and then we'll check and make sure everything works. PO4, 2. Okay, remember this is the problem, and then this is where our solution is. Okay, so now I've done that. The phosphates match on both sides, the magnesiums match on both sides. What doesn't match is the NaCl, so plus, and let's see how many I have on this side. So 2 times 3 for the Na would be 6 Na, and then also 2 times 3 for the chloride, but they are together, so total 6 sodium and 6 chloride. combine. All right, and that's salt. So you'll typically see them paired ionic bonded. They're bonded ionically. Okay, so that is a balanced chemical equation for the combination of sodium phosphate and magnesium chloride. All right, and that's a little tougher. You'll do some practice. You'll get it. Let me know if you need any help. Okay, so another thing that you have to kind of pay attention to is the charge. It can kind of help you determine what's going on. Oh, let me pull the book back up. So you'll see here that sodium carries a plus charge. That's because we were talking about valence electrons. It likes to give up that electron and become positively charged. Excuse me. So phosphate has a negative 3 charge. Right. So when all of these, looking back at our problem we just did, if I were to put charges on all this, so the Na would have a plus, the Cl would have a minus. Those would all balance. 6 plus charges and 6 minus charges would balance. The phosphate has a 3 minus charge. All right, 3 minus charge. Okay, so that matches up here with the 3 sodiums, which has a 3 plus charge. Magnesium has a negative or plus 2 charge, I believe. So the fact that chlorine has a negative 1 charge, we said there's 2 there, so that negative 2 would balance. These charges are also balancing at the same time, and well, they combine based on the charges, right? That reaction happens because the charges can be interchanged. All right, let's get into that. These are different types of reactions. All right, so combination reaction, I put 2 things together to make one item. That would be like the bike, right? I had the wheels and the frame, put them together, I made one bike. That's a combination. A decomposition would be the opposite. I had the bike, I broke them down to sell parts, sold my tires, sold my frame. It was a decomposition of the bike. A single replacement, you can kind of pay attention to these based on these. It'll have a single change, right? So zinc is by itself. Then on this side, hydrogen is by itself. I've only moved one reactant in the equation. I've only flipped one reactant versus a double replacement where you'll see like sodium hydroxide, hydrogen chloride. I've switched chlorine over to the sodium, and I've also switched a hydrogen over to the hydroxide to make water. So 2 different items are being swapped. It's pretty straightforward. So combustion reaction, anytime something's burned, so I like to think about burning as just being, nothing burns without oxygen, right? So you have to have, or some type of fuel present. Oxygen has to fuel the fire. So any hydrocarbon, you'll see here in your book, it's like CH4, which is a methane. Propane would have 3 carbons. Butane, 4 carbons, and we know that like those are prefixes that tells you how many carbons are in there. All these are gases. They're also fuels. So you burn it, you add oxygen, it produces water and carbon dioxide every time. And that's a combustion reaction. This little symbol here is heat. So that's like the flame. I apply a flame with oxygen in the presence and a fuel. It produces carbon dioxide and hydrogen. Those are easily recognizable. You'll see that anything plus oxygen, applied heat, that's a combustion reaction. You're going to automatically think carbon dioxide, water, or my products. That is also an example of an oxidation reduction reaction. We call these redox reactions. They have to do with the transfer of electrons. So I've never used this oil rig anagram or whatever, but so oxidation is a loss of electrons, meaning that it's getting more positively charged, right? And a reduction gains electrons and gets more negatively charged. All right, and so like you'll look for certain key things that tells you a change in charge is taking place. So for this first example, two things come to mind. So copper and solid form, anything. Oh yeah, let me back up just a little bit. Yeah, these symbols are for telling you what the state of matter. They're the state of matter for the molecules or atoms that you're talking about. Okay, let me clear this off. There is a clear off. So this table right here on the left side of page 228 talks about all the different symbols you're going to see in a balanced equation or in chemical equations. Excuse me. So S is just solid. All right. If you see this, you can automatically assume that it has a zero charge. Okay, zero charge. That means it's balanced. Okay. Any solid is automatically balanced, and the same can go for liquid and gas. Okay. So anything in solid, liquid, gas form is a balanced molecule or atom, and it has a zero charge. So all these, zero charge. Ten-four. So the only ones that you're going to associate with charge is the one that's AQ. AQ looks like this. Okay, and it stands for aqueous, meaning that it's been broken down in solution. So solid is going to be, you know, anything solid particles, gold, copper, metal. Gas, obviously, like chlorine, hydrogen, oxygen, nitrogen. These things, the diatomic molecules, in a lot of cases. But if it's represented with a G, that means that it has no charge. Okay, that means it's just in its natural form. Okay. Now the AQ is to represent something that's been dissolved or broken down in solution. All right, and that's what L is. L is the solution. Okay, so the only time you'll ever see L is behind water or maybe different kind of solvents, but for the most cases in your coursework, L will only be used for water. I think it's used for acetic acid and some other solvents that you may see, but just know that it doesn't have a charge, and everything that is dissolved in water is represented with AQ. Okay, so back to this. That table right there kind of talks about all that. It also says the yield sign, plus sign, heat. So this is kind of a little legend to remind you how to use these in chemical equations. So back to where I was, redox reactions. Okay, so remember I said zero charge. So this equation here has zero charge, but something has obviously happened because an oxygen, so let me show it to you in this way. Clear this. Alright, remember we said that oxygen, when bonded in a diatomic molecule, alright, 1, 2, 3, 4, 5, 6, yeah. I fucked that up. Okay, so remember when oxygen is bonded in a double bond. I don't know what I'm doing. So I have to put a lot of energy into this to be able to break that bond. And when I do break that bond, it's going to leave me two short of electrons. Hold on just a second. When I do break that bond, these two are going to go over here, and these two are going to go over here. So I'm back to the unstable molecule that I had in the first point. Okay, so I know I'm putting energy in there. That energy is it comes from the transfer of electrons. Okay, so that's what's happening in a redox reaction. And you'll see here, so when the oxygen is separated, remember it was two shy of valence electrons. So it's going to take the two valence electrons from the copper, and that's indicated right here. All right. The copper gives up 2 electrons, becomes copper 2 plus. I don't like how it's represented with the solid there. Like I said, I typically think about that being in solution. I guess it doesn't have to be, but so just keep that in mind. Yeah, like these are all written with the aqueous. That's how I'd like to see it. I wouldn't agree with the way the book is doing this. But in any case, so the 2 electrons are given up from the copper, creating that 2 positive charge, and they were donated to the oxygen to fill that valence shell. And so a reduction of the oxygen, remember reduction is gaining electrons, and then an oxidation of the copper. All right? But everything else is just balancing equations. All right? So you'll use the charges the same way that you use the coefficients. You find the least common multiple. In the case with zinc and copper, looks like 2 actually might work. So that'd be just straightforward. You do replacement. Yep. Pretty simple and straightforward. I'm sure you'll have more difficult ones on your master in chemistry. Okay. So we're starting to drag a little bit. I'm going to try to get finished with this. Mole relationship and chemical reactions, chemical equations. So if nothing is being lost as a gas, the conservation of mass will prevail, right? So the same weight or mass that I have in the reactant sides will be the same weight that I'll have on the product side. So that's given that all the reactants were used, everything's there. I didn't lose any in gas. The weights will be the same on both sides. And so that'll allow us to do math equations using molar mass, right? So we said molar mass is a weight that we can interpret into a mole to get an amount. How much of a substance we have. Not just the weight of it, but actually how many little particles are in there, because when we start mixing molecules, particles, or atoms, you want to have the right mixture, right? It's just like bacon. I mean, if I put too much baking soda, my final dish is going to be gross, okay? It's not going to be what I expected it to be. So you have to have the right amounts. We know the amounts with the moles, molar mass. And this will go into those in detail. You'll have some more practice on that. Yeah, I think you should have it. I'll do some more practice on that another time. Maybe in the review, like I did a review for specific heat last time. I'll probably do. Let me know if you have problems with these kind of math problems, or this kind of math work, and I will post a video, do some more examples. Let me know if you have certain questions on mastering chemistry. I can go in there, look at those, maybe do videos on working those problems out. Okay, so in exothermic, endothermic, activation of energy. Yep, I need to touch on this just a little bit. So when you're going through a reaction, I said, well, let me bring this iPad back in. Where's my... Okay, this oxygen, for example, clear it. The oxygen is double bonded, and it takes energy to split these bonds. This is my Lewis dot structure, if you haven't practiced that yet. Excuse me, just a second. So the activation energy is the energy that I have to put into this right here. What was I mixing it with? I can't even remember. It was a combustion reaction, so hydrocarbon, CH4. Okay, so the energy that I have to put into this reaction, let me clear this off. Okay, so these two atoms, these two molecules here are not going to combine on their own. I have to put a bunch of energy into it with them next to each other, and it'll cause a reaction. The energy that I put in is that heat, right, the flame, and then when I get done, I have H2O and carbon dioxide, gas liquid. Okay, so that energy requirement is called the activation energy. It's the energy needed to cause a reaction. Now this table here on the top of 247 kind of shows how a reaction occurs over time. So I have to put more in it. You'll see here the energy goes up. I have to put in energy until it reaches a certain point. Then the reaction occurs. Now when the reaction occurs, it's rearranging to lower the energy. Okay, that's it might get a little confusing when you say it like that. I have to put energy in to lower the energy later, right? But the reaction happens, and I might get something beneficial out of the one side, right? Like I'm making an antibody on this side, but I need to react all these chemicals on the reactant side. So I have to put a bunch of energy, heat or electricity or hydrogen protons, right? Some kind of energy into this system to get all these reactions to start taking place. That's called the activation energy. And you can the heat, whether or not the heat is gained or lost on the reactant side will tell you whether or not it's endothermic or exothermic. I like this reference to cold packs and hot packs. That's a good way of thinking about it. So when I get the little heat pads that you put in your shoes in the winter or whatever, and I bust them down, rub them, or whatever you do to activate it, it gets hot. So a reaction is taking place and heat is being given off. Now conversely, there's also the cold packs. Okay, so the cold packs draw in the heat from the environment. It absorbs the heat. That would be an endothermic reaction. So that can be kind of confusing, and we'll put some practice on Mastering Chemistry that kind of deals with that and gives you some more practice. All right. A catalyst, just quickly, last thing I guess. A catalyst lowers that activation energy, and that's the most important thing to know about this particular section. Is like I said, when I was if I'm making an antibody or something, but I have to put a lot of energy into that reaction to get it, I might start looking at ways to lower the amount of energy. Say it costs me $10,000 to power the electricity needed to run my reactor, because the activation energy is so high for this particular reaction. Well, what if there was a way for me to add a metal in the reaction or something else that helps me save $5,000 in electricity costs? And it does that by lowering the activation energy. All of a sudden, I didn't have to I didn't have to heat it up but to 20 degrees instead of 120 degrees, and my reaction started occurring. That happens because the catalyst lowers that activation energy and allows me to get over that hump quicker. Okay, so the illustrations are really good here. As far as thinking about how the energy cycle works in these reactions, I had to put some energy in, but I save it on the back end. In other cases, I'm making something that will put out the energy on the back end, like the heat pack. So I'm conserving all that energy in this little pack. When I break it, it lets go all that heat, and so the reaction is exothermic. It's a really good way of thinking about endothermic versus exothermic. All right. So I will post something for lab, get the Mastering Chemistry done as well. And I will see y'all next week. Peace.